reactivity. So we'll be seeing what kind of chemical reaction this cycloalkane will show. So there are no such number of chemical reaction, only some countable number of chemical reactions this cycloalkane show. As you know, alkane is very non-reactive. That's so cycloalkanes are also that show the same property, and these are not so reactive. So whatever alkane shows the property, the same properties are shown by cycloalkane. The first property, you'll be seeing the substitution reaction with halogen. In presence of sunlight, it undergoes substitution reaction. And one more thing, the lower alkanes are not stable. The lower alkanes are not stable because of some strain. So that what is the strain, that we'll be discussing afterwards. So because of strain, this will behave like a alkene. Okay, so that's why it can show how the alkene are showing the addition reaction. So addition reaction of hydrogen will be seeing, addition reaction of halogen will be seeing, and one more thing, addition reaction of halogen acid. So these are the chemical reaction we'll be seeing in cycloalkane. Substitution reaction with halogen. So how the cycloalkane shows substitution reaction? So if you take any cycloalkane, so what will happen if you and these are the halogen, right? So these are the halogen molecules. So whenever you are taking halogen molecules and you are taking cycloalkane and you are giving light, so what will happen, this cycloalkane will undergo substitution reaction. So this basically, this will remove one hydrogen molecule. So if there is a hydrogen molecule is attached here, so everywhere two hydrogen molecules are attached, right, to every carbon atom. So it will go and remove one hydrogen molecule and replace the hydrogen molecule. So you can see here. So basically this one is a cyclohexane. So what is this? Hello cyclohexane. Hello means basically if it is a bromine, then bromocyclohexane. If it is a chlorine, then chlorocyclohexane. Similarly, this is a cyclopentane. The same thing happens here. So chlorocyclohexane or bromocyclohexanes, right? So so the chemical reaction, if you see, it does not react with acid, base, oxidizing agent and reducing agent. So cycloalkane or alkane do not show any kind of reaction with acid, base and oxidizing or reducing agent. And higher alkane above 4. Okay, so you can see here hexane, pentane, so above 4. Basically these kind of alkane, so hexane, heptane, octane, decane, so these kind of cycloalkane show substitution reaction, and lower alkane show addition reaction like alkane. Why they will show addition reaction, we'll discuss whenever we study about the strain, right? Kind of reaction they are showing. So you can see here, basically there is a bond, there is a carbon carbon bond, right? So imagine that you are very stable whenever you are sleeping straight. Okay, you are very stable whenever you are sleeping straight. So somebody is coming and telling you that no, you should not sleep like this, you should sleep like this. Okay, you should fold your leg or you should fold your hand and you should sleep like this. So what will happen, you will be sleeping like this for some time, but you, as you know, you are not stable, right? So somehow what you will do, you will try to straight your leg or straight your hand, and you try to come to this posture, right? The similar thing happens with this case also. So you can see here, basically this is a 3 carbon atom compound. Try to, so it always shows, it always search for its freedom, right? In whichever way it is flexible, in that way it wants to stay. So if you stay, if you try to put it in a ring structure, then it has to be like this structure only. It cannot become straight, right? So in any way, if it try to become straight, it cannot do that. Okay, right? So but in this way also it is unstable. Okay, this is unstable. So you can imagine the situation that you want to be straight, you want to be sleep in straight position, okay, in this position, but somebody is telling you to sleep in this position. So what you are doing, you are sleeping, and after some time you are coming back to this position. So what that fellow will do, since you are not stable in this position, to make you stable, that fellow will do, that fellow will bind. Okay, that fellow will bind in such a way that you cannot move from this position. So what will happen, basically you will be unstable. So what you will be looking for at this point of time, so you will be looking for any opportunity. If somebody comes and if he or she helps you in folding in removing this removing from this trend, you can easily go to this state, right? So every time you will be looking for this opportunity. Similarly, in case of cycloalkane, they will be the lower cycloalkane, they will be looking for the opportunity. Whenever the opportunity comes, they will unfold, right? They will unfold. So basically, whenever you are doing the hydrogenation, what will happen? One hydrogen will go here and one hydrogen will go here. Okay, they will satisfy the bond, they will satisfy the valency. That's how this bond will break. This bond will break and they will open up. So whenever they will open up, from the cycloalkane they will form the normal alkane or straight chain alkane. This is the addition of hydrogen. Similarly, addition of halogen. In case of halogen, also the same thing. So always they will be looking for the opportunity to unfold, right? So whenever such kind of compounds comes, they will look for the unfolding, and they will become the normal what? Normal alkane. So one x will come to this part, and one x will come to this part, and this bond will break, right? So two this bond, particularly this bond, not this bond, okay, not this bond, particularly this bond. So what will happen? There is a x and there is a x attached. Similarly, in this case also the same thing. Okay, so one x will come here and one x will come here, and this bond will break, right? This bond will break, and you will get the compound like this. And addition of halogen acid. In this case also the same thing. In one part, what will happen? In one part, hydrogen will be attached. In one part, hydrogen will be attached, and in the other part, the halogen will be attached. Okay. So in other part, halogen will be attached. So that's why you have a halogen here, you have a halogen here. Since why I have not mentioned hydrogen here? Because hydrogen you are not mentioning whenever you are writing the skeleton, right? The reaction. So Bayer strength theory, what is it? What is Bayer strength theory? Okay, so the first thing you should know about Bayer strength theory, it explains the stability of cycloalkanes and assumes all atoms lie in the same plane. Okay, all atoms lie in the same plane. The all atoms lie in the same plane. So here we'll get to know what is a strain for a compound. What is a strain for a compound? And Bayer strain. So what is Bayer strain theory? Bayer is a scientist. So it talks about the strain in the compound, and the way he approached the strain in a compound, that way is known as Bayer strain theory. Okay, so what Bayer strain theory talks about, it explains the stability of cycloalkane. Okay, and what it assumes all the in the cycloalkane, all the carbon atoms which are forming the ring. Okay, all the carbon atom which are forming the ring lie in the same plane. Okay, and the second point, the deviation from normal tetrahedral angle of ring carbon atom is called as angle strain. Okay, so what is the angle strain? Basically, if you know, a carbon atom in the cycloalkane or alkane is a tetrahedral carbon atom. Is it sp3 hybridized, and it is a tetrahedral carbon atom. So as you know, tetrahedral angle is 109 degree 28 minute. But whenever an alkane becomes cyclic in structure, so those tetrahedral angle is not at all retained in the carbon bond. Okay, so we'll be seeing here in the next part how the angle is deviated. Okay, so more the angle strain, more unstable is the compound. So what is a Bayer strain theory? It is a theory which explains the stability of alkane. So what it is telling? So the deviation from the normal tetrahedral angle of the ring carbon atom is called as angle strain. More the angle strain of a compound, more unstable is the compound. Okay, and one more thing you should remember. Oh, this is a very important point. It fails beyond the cyclopentane. So up to cyclopentane it is fine. Up to cyclopentane it is fine. But whenever you are going beyond cyclopentane, if you talk about cyclohexane, cycloheptane, cyclooctane, so this theory is not valid. Okay, so how can you find out angle strain? This is the formula: normal tetrahedral angle minus distorted angle divided by 2. Okay, I'll give you an example how you can find the angle strain. So let's look at this example. Okay, this is a very important information. You should know how you have to find out the angle strain. Tetrahedral angle, that is the 109 degree 28 minute, this is always constant, and distorted angle, what is the distorted angle? Divided by 2. This is how you have to calculate the angle strength. So now look at this compound. This is a cyclobutane, right? In cyclobutane, this bond, any bond, right? In any bond, this is a sp3 carbon atom. This is a sp3 carbon atom. So you can see here, whatever carbon atom is here, that is sp3. Whatever carbon atom is here is sp3. So this bond is 90 degree. Okay, so all the bonds are 90 degree, but you know the tetrahedral bond angle is 109 degree 28 minute, right? So basically this is a 90 degree. Okay, this is not 900, this one is 90 degree. So whenever you see this kind of this kind of structure, basically this carbon atom is stable when it has the bond angle 109 degree 28 minute, right? But it has the bond angle 90 degree. So what it will always try to do, it will try to expand the bond angle, right? It will try to expand so that it can go and reach to 109 degree 28 minute. That's why it will always put a strain on the molecule. Okay, so basically what is happening, because of this bond, this molecule is a cyclobutane. But what this carbon atom is telling, no, you should not stay in this state, you should go to 109 degree 28 minute. So it will be always looking for the opportunity. Whenever it gets the opportunity, this bond will break. Okay, so this is what the angle strain. So the normal carbon atom, from the distorted angle, it will try to go to the normal tetrahedral angle, right? So because of that, it will cause some strain to the compound, okay, or instability to the compound. This is known as angle strain. So how you can find out the angle strain? Angle strain equal to tetrahedral angle minus distorted angle divided by 2, that is 9 degree 44 minute. Okay, so we can find out the other example. You can see here, this one is a cyclopropane. In this case, the bond angle between carbon. So you can see here, this is a carbon, this is a carbon, and this is a carbon, right? This one is also a carbon. So between this carbon and carbon, bond angle should be 109 degree 28 minute. But in this case, bond angle is 60 degree, right? So what is the angle strain? You can see here, angle strain is coming out to be 24 degree 44 minute. 24 degree 44 minute. If I'll ask you which molecule has more angle strain, so obviously this molecule cyclopropane has more angle strain than cyclobutane. So now if I ask you which compound is more stable, so as I have already told you that more the angle strain, more unstable is the compound. So in this case, angle strain is more, angle strain is less. So more unstable cycloalkane is compared to cyclobutane. So you can say also that cyclobutane is more stable than cyclopropane. This is all about Weber strain. So now we'll see SAS more theory. So what this theory explains? So it explains the stability of cycloalkane beyond cyclopentane, right? It explains the stability of cycloalkane beyond cyclopentane. The next point, rings with 6 or more carbon atom are not planar but they puckered. Puckered means they will go to some different kind of structure. Okay, in whatever structure they are expected to stay, they will not stay in that structure. They will go to some another structure. Basically, this phenomenon is known as puckered. Okay, so basically structure is known as puckered structure. And what is this? The ring with 6 or more carbon atoms are not planar but they are puckered. Okay, so this Sartre-Morse theory, it explains the stability of cycloalkane beyond cyclopentane. Okay, and uh, and this rings with 6 or more carbon atoms are not planar but they puckered rings. And rings free from angle strain are known as strainless rings. Rings free from angle strain are known as strainless ring. So this is all about Sartre-Morse theory. If you see about cyclohexane, so cyclohexane can so we expect cyclohexane to be in planar form, but in reality cyclohexane do not stay in the planar form. It always stays in the it always stays it always stays as the chair form. You can see here, so it has different conformations. So different structure it attains, those are called conformations of cycloalkanes. So basically it stays in chair form. Basically it is looking like a chair, right? And it stays in half chair form. This part you can see here, it is going to this part. Okay, half share form, then twist port, then again half share, then board form. This is how the transition will occur. This is how the transition is going to occur, right? From chair form it will go to half chair, from half chair it will go to twist port, from twist port again it will go to half chair, and it will become board form, right? Cyclohexane. And one more thing, it is very important to know for you. So whenever cyclohexane is in chair form, okay, chair form. So you can see here, this is a chair form. This is a chair form. So in this chair form, the two hydrogen which are present on this on each carbon atom, one hydrogen go towards top and another hydrogen go towards down. Okay, one hydrogen go towards top and another hydrogen go towards down. So basically those hydrogen which are going top, okay, which are going top. So you can see here, this is the ring carbon atom, vertex carbon atom. One carbon atom is going down here, okay, exactly down. You can see here exactly down, and in this case exactly top. So I have mentioned this, I have mentioned all the carbon atom which are going exactly down or exactly top in red ink, and I have marked those hydrogen which are going not exactly top or not exactly down, in between them. So in between that, those are called equatorial hydrogen atom. Basically these are the hydrogen axial hydrogen atom, these are the equatorial hydrogen atom, right? So axial hydrogen atom and equatorial hydrogen atom. So basically cyclohexane, what will happen, it will flip. So you can see here, this carbon atom from down it has moved to top, right? So basically cyclohexane, what it will do, it will go from one structure to another structure. This is a chair form, this is also a chair form, but there is a difference in this chair form. You can see here, this carbon atom is down, in this case this carbon atom is top. So this moment or this transition from one chair form to another chair form is known as what? The flipping of ring, the ring flipping. This is known as ring flipping. So this is the one important term, this is called ring flipping. So whenever ring flipping happens, what will happen, this axial hydrogen will become equatorial hydrogen, and this equatorial hydrogen will become axial hydrogen. This is the important phenomena what exists in cyclohexane. Now we'll see what is pizza strain. So for pizza strain, I am just giving you a scenario which will be helpful for you to understand the topic pizza strain. Okay, so look at here. This is a road. Okay, a road or whatever you can think. So this is a platform, right? So on the top of the platform, one fellow is there who is very rude. Okay, he doesn't want anybody with him. Okay, anybody to compete him. Suppose in this place one more fellow is coming, okay, who is also having the same mentality. Okay, basically this fellow doesn't want any fellow to be around him, and this fellow also doesn't want anybody to be around him. So whenever these two fellows will meet, what will happen, basically there will be a repulsion between these two fellows, right? So this fellow will tell you go stupid fellow, and this fellow will tell you go stupid fellow. Basically there is a instability of these two fellows. Okay, there is a instability, so nobody can work here, right? So this is a working platform, and this fellow is here who doesn't want anybody to come around him, and this is also a one more fellow who doesn't want anybody come around him. So whenever these two fellows are together, they cannot work or they are not stable. Okay, but what happens is a platform wherever this fellow is working who doesn't want anybody to be here, and there is one more fellow, okay, but he is in another platform. Okay, so he also doesn't want anybody to be there around. So what will happen, whenever these two fellow are just exactly opposite to each other, okay, so nobody is disturbing anyone. Okay, so what will happen, in this way this fellow can work here and this fellow can also work here, right? So basically in this case the system is stable, or these two fellows are stable. Okay, so similarly same kind of phenomena you can see in the compound. Basically see here, this one is a 1,3 dichloropropane, 1,3 dichloropropane, 1,3 sorry 1,2 dichloro ethane, 1,2 dichloroethane, right? So you can see the compound here, 1,2 dichloroethane. So basically this is a chlorine atom, this is a chlorine atom. So chlorine atom, three lone pairs are there. So you can see here three lone pairs are there. So these lone pairs, what will happen, these lone pairs and these lone pair try to repel each other, so whenever they will repel, they will go to a distance So they will go to some distance wherever the repulsion is minimum. They want to stay in that distance. Okay, so whenever this chlorine atom and this chlorine atom is exactly behind with each other, there is a maximum repulsion. So they want to go to minimum repulsion. How they will go to minimum repulsion? Basically, this chlorine atom has to come here. This chlorine atom has to not here. This chlorine atom has to come here, so that they will stay in maximum distance with each other. Okay, they will stay in maximum distance with each other. So what will happen whenever this kind of platform comes? So what will happen, this chlorine atom will repel this chlorine atom. That's how this chlorine atom will move to this state. Okay, so this area. Okay, and whenever this position has occurred, the compound has added this position, there is a strain. Okay, why there is a strain? Because this chlorine atom, they will be trying to repel each other, and this strain is known as torsional strain or Pizzer strain. Torsional strain or Pizzer strain. So you can see here, basically in this case, chlorine atom to chlorine atoms are exactly behind with each other, right? That's why there is some kind of repulsion between them, and because of that repulsion, there is a strain called Pizzer strain is happening. Okay, this strain is known as Pizzer strain. So what will happen in this case, this chlorine atom will come down, so that this chlorine atom and this chlorine atom will come down somewhere here. So that's how chlorine atom, these two chlorine atom will be far away from each other, and there will be repulsion between them will be minimal also. Basically, this is the cyclopentane. As you know, each carbon atom is having two hydrogen. One hydrogen is top and one hydrogen will be bottom. Okay, in this case also one hydrogen will be top and one hydrogen will be bottom. So whenever this is the structure it will attain. I have showed in two carbon atom. Basically, in every carbon atom there will be a hydrogen will be present. Okay, so whenever cyclopentane will acquire this kind of structure, basically there is a repulsion between these two hydrogen, right? There is a repulsion between these two hydrogen. So because of the repulsion, this cyclopentane ring will not stay in this state. Because of this repulsion, this cyclopentane will not stay in this state. What kind of structure will get? You will be getting a structure like this. So basically, four carbon atom will remain in one plane, and one carbon atom will go out of the plane. One carbon atom will go out of the plane. So this is called open book structure. So cyclopentane has open book structure. Why this is happening? Because of the Pizzer strain. Look at the thing, what is a Pizzer strain? So Pizzer strain is the torsional strain, okay, which is produced due to the repulsion of non-bonded electrons of atom, which is produced because of the non-bonded, which is produced due to the repulsion of non-bonded electrons of atoms. Okay, although cyclohexane do not have any single strain, any angle strain, but it is occurred due to the torsional strain. As I told you that cyclohexane has torsional strain, although it is not having any angle strain, it is having torsional strain. That's why it will go from the normal structure to a open book structure, right? So that's what our topic about today, and we'll see the next topic. Till then, thank you all of you for your patient listening. Yeah, thank you.